At scales far smaller than anything visible to the unaided eye, the world behaves in ways that gently resist everyday understanding. Properties refuse to exist independently. Measurements create rather than reveal. What feels solid dissolves into tendency rather than certainty. Welcome to Sleep Knowledge. If you find comfort in exploring questions that lie beneath the surface of ordinary experience, settle in and let these ideas unfold slowly. And if you feel moved to, share where you are drifting off tonight. It is always warming to know how far these quiet thoughts travel. At the smallest scales physicists have managed to probe, familiar assumptions begin to soften without drama. The definite gives way to the probable. Location spreads into regions. Boundaries between objects blur at the edges. Even the distinction between something happening and nothing happening becomes less clear than intuition would suggest. For more than 100 years, experimentalists have mapped this territory using instruments designed for exceptional precision, chambers that detect individual interactions, lasers cooled until vibration nearly stops, mathematical frameworks refined not to comfort intuition but to remain true to what nature consistently shows. What has emerged is not randomness, but a different kind of order, one that defies expectation yet proves extraordinarily reliable. Predictions confirmed to many decimal places, devices built on principles that feel strange, yet perform their functions quietly, every day. Research institutions across continents continue to extend this understanding, pushing measurement deeper, exploring ever more delicate conditions, and finding again and again that the same patterns hold. With each refinement, the picture becomes clearer, even as its implications become more subtle rather than more settled. This journey moves patiently through that landscape, not to force understanding where it resists, and not to simplify what cannot be simplified, but to follow quantum behavior where it leads, to see what experiments reveal, what theories predict, and where certainty naturally gives way to something more open. Settle in. Let the quantum world unfold gently. Human perception evolved to solve specific problems. It needed to distinguish predator from prey across an open landscape. It needed to judge whether a branch would hold weight. It needed to estimate distance well enough to throw accurately or catch reliably. These capacities developed over vast stretches of time, shaped by survival rather than by truth. What perception was never designed to do is describe reality at scales millions of times smaller than anything ancestral humans encountered. The brain constructs its picture of the world from repeated experience. Objects appear to stay where they are placed. Surfaces feel continuous and solid. Causes lead to effects in clear sequence. Motion follows smooth paths that can be traced and predicted. These patterns get reinforced so often that they stop feeling like interpretations. They feel like direct access to reality itself. It becomes difficult to imagine that the world could work any other way. And so when experiments at atomic scales reveal behavior that contradicts these deep patterns, the natural response is not curiosity but discomfort. At very small scales, intuition begins to mislead almost immediately. The assumption that an object must always have a definite location feels obvious until nature refuses to cooperate. The expectation that things move along continuous paths works beautifully for thrown stones and orbiting planets but quietly fails when electrons and photons are involved. This failure does not happen because the universe becomes chaotic or unreliable at small scales. It happens because human intuition was never built to function there. Natural selection rewards practical effectiveness, not philosophical accuracy. A mind that quickly assesses threats survives. A mind that ponders probability distributions at atomic scales gains no advantage in most environments. As a result, perception simplifies ruthlessly. It compresses vast amounts of sensory data into manageable summaries. It discards detail that does not immediately matter. It builds models that are good enough to navigate the world successfully, even if those models are incomplete or technically inaccurate. Consider how limited the senses actually are. Vision detects only a narrow band of electromagnetic radiation. Most of what exists remains invisible. Hearing registers vibrations within a specific range, ignoring everything outside it. Touch averages over countless microscopic events to produce the illusion of smoothness. None of these senses report reality in full detail. They report edited versions optimized for usefulness. Quantum physics operates far below these edited summaries in a regime where the shortcuts perception relies on no longer apply. Behavior that feels strange or paradoxical is not illogical. It simply refuses to conform to expectations that were never meant to describe it. When experiments show that certain properties cannot be measured simultaneously with arbitrary precision, this conflicts with the assumption that everything about an object exists definitively at all times. When particles display characteristics of both waves and discrete units depending on context, it feels contradictory even though it represents a consistent description supported by observation. The history of physics shows this pattern clearly. Classical mechanics once appeared complete. It explained the fall of objects, the motion of projectiles, the orbits of planets. Yet as instruments improved and measurements became more sensitive, small inconsistencies appeared. These were not experimental mistakes, they were signals that familiar concepts were being stretched beyond their appropriate domain. By the early 20th century, this tension could no longer be ignored. Experiments examining heat, radiation, atomic structure, and light itself produced results that simply refused to fit existing frameworks. Scientists trained in classical methods found themselves facing data that demanded something fundamentally new. The discomfort was not trivial. Many of those who helped develop quantum theory expressed frustration with where the evidence led. Max Planck regarded his own breakthrough as a mathematical convenience rather than a physical truth. Niels Bohr struggled to articulate what quantum descriptions actually meant. Albert Einstein, despite contributing crucial insights, remained uneasy with probabilistic elements throughout his life. What is often forgotten is how carefully this discomfort was handled. Quantum theory did not arise from speculation or philosophical preference. It emerged because experiments left no other option. Measurements carried out independently in different countries produced consistent results that defied classical explanation. The theory developed not by abandoning rigor, but by expanding what rigor needed to include. This distinction matters deeply. There is a temptation to interpret quantum physics as evidence that the universe is fundamentally irrational or that anything is possible. In truth, it is one of the most disciplined theories ever constructed. Its predictions are among the most accurate in all of science. Technologies relying on quantum principles work with astonishing consistency. From the devices that regulate global communication to the systems that enable modern medicine, strangeness does not imply instability. It signals unfamiliar structure. Accepting this requires adjusting expectations rather than abandoning logic. Instead of asking why quantum behavior contradicts intuition, it becomes more useful to ask why intuition should be trusted at scales it was never designed to navigate. Just as human vision cannot detect infrared light without assistance, human intuition cannot grasp atomic behavior without guidance. Instruments extend perception. Mathematics extends reasoning. Together, they provide access to domains that would otherwise remain closed. This process can feel disorienting initially, particularly when long-held assumptions are challenged. Yet, it is also profoundly human. Science advances by recognizing the limits of what feels obvious and allowing evidence to guide understanding forward. Each time intuition reaches its boundary, space opens for deeper knowledge to form. There is quiet reassurance in this. The universe does not adjust its rules to match human comfort. It behaves consistently, patiently, and without concern for expectation. When intuition fails, it is not because reality is broken. It is a reminder that understanding must be extended rather than assumed. By recognizing early that intuition has limits, it becomes easier to approach unfamiliar ideas without resistance. Confusion stops feeling like a problem requiring immediate resolution and becomes instead a natural stage in learning something genuinely new. The discomfort fades, replaced by curiosity. And with curiosity comes willingness to let observation speak even when it whispers something unexpected. From this perspective, the limits of intuition are not obstacles. They are markers. They show where everyday experience ends and deeper structure begins. Beyond that boundary lies not disorder, but a quieter, more subtle order, waiting to be understood on its own terms. Solidity feels convincing. A wall resists pressure, A floor supports weight. Objects have heft and permanence. From the earliest moments of physical awareness, matter presents itself as firm and continuous, assembled from pieces pressed tightly together. This impression is reinforced so consistently that it rarely invites questioning. Matter feels solid because at human scale, it behaves that way. Yet, when examined more closely, that conviction begins to dissolve. At the level of individual atoms, solidity fades into something far more delicate and surprising. An atom is not a miniature version of everyday solidity. It is mostly empty space, vast stretches of it, relative to the tiny structures that give it identity. If an atom were expanded to the size of a football stadium, the nucleus at its center would be no larger than a marble resting at midfield. The rest would be open volume, sparsely occupied by regions where electrons might be found but rarely pinpointed to exact locations. This runs directly counter to intuition. Empty space usually means absence, nothingness, lack of substance. Yet atoms, despite being overwhelmingly empty, combine to form materials that feel unquestionably solid. The key lies not in volume, but in interaction. Forces, not mass, create the sensation of solidity. Early models of atoms did not begin with this picture. Throughout much of the 19th century, atoms were imagined as indivisible spheres, solid and simple. They were useful for chemistry as bookkeeping tools, but carried no implication of internal structure. This view began to change as experimental techniques improved and questions grew sharper. One of the pivotal moments came through work led by Ernest Rutherford in the early 1900s. His team directed streams of charged particles at thin sheets of gold foil, expecting minor deflections consistent with a soft, diffuse distribution of charge within atoms. Most particles passed through as anticipated, but a small fraction scattered at sharp angles. Some even rebounded backward. The result was so unexpected that Rutherford compared it to firing artillery shells at tissue paper and seeing them bounce back. The implication was unavoidable. Atoms contained a tiny, dense core where most of their mass resided. This nucleus occupied only a minuscule fraction of the atom's volume, yet exerted enough influence to dramatically alter the paths of incoming particles. The rest of the atom had to be largely empty, offering little resistance. This discovery dismantled the idea of atoms as compact units. It replaced that picture with a structure that was mostly absence, punctuated by concentrated centers. The result was not philosophical speculation. It was a conclusion forced by experimental evidence. Matter, it turned out, was already stranger than appearances suggested. Niels Bohr extended this picture by proposing that electrons occupied specific regions around the nucleus associated with particular energy values. While later refinements would replace simple circular paths with probability distributions, Bohr's work provided a crucial foundation. It showed that atomic structure followed precise, constrained rules that bore no resemblance to classical expectations. What is striking is how quickly this strange architecture proved useful. Once atomic models were adjusted to reflect experimental reality, they began explaining chemical behavior with remarkable accuracy. The periodic table gained deeper meaning. Spectral lines, once mysterious, became signatures of atomic transitions. The emptiness within atoms did not make matter fragile, it made it comprehensible. So why does solid matter feel solid at all? The answer lies in interaction rather than occupation. Electrons in one atom resist being pushed into the same states as electrons in another atom. Electromagnetic forces create powerful repulsion at close distances. When a hand presses against a table, the sensation arises not because atoms touch like marbles, but because electron clouds resist compression with tremendous strength. What feels like contact is actually a standoff between forces. In this sense, solidity is emergent. It arises from countless interactions governed by underlying rules, not from material packed edge to edge. The same principle explains why steel supports weight while air does not. Despite both being composed of mostly empty atoms, structure and arrangement matter far more than density alone. There is subtle comfort in this realization. The world does not lose its reliability when examined closely. Chairs remain dependable. flaws continue to hold. The emptiness within atoms does not undermine everyday experience. It simply reveals that experience rests on deeper mechanisms, operating quietly without demanding attention. This perspective also serves as a concrete example of intuition meeting its limit. At human scale, assuming solidity works perfectly well. At atomic scale, it misleads. Neither view is wrong within its proper domain. Problems arise only when one is stretched beyond where it applies naturally. Recognizing this makes it easier to accept that familiar concepts may need adjustment without being entirely discarded. There is gentle humor in how misleading appearances turn out to be. A seemingly solid wall becomes a delicate arrangement of mostly empty atoms, held together by invisible forces, behaving with unwavering consistency. It is not the sort of emptiness associated with fragility or collapse. It is structured emptiness, disciplined and reliable. Scientific institutions around the world continue refining this understanding, using increasingly precise instruments to probe atomic and subatomic structure. Particle accelerators, spectroscopy techniques, and imaging methods all confirm the same basic picture. Matter is stable not because it is filled, but because it is governed. By confronting the emptiness at the heart of matter, a deeper lesson quietly takes shape. Reality does not need to conform to appearances in order to function beautifully. The assumption that matter must be compact and solid dissolves under scrutiny, replaced by a subtler and more elegant framework, one where space, force, and probability combine to produce the familiar world without ever quite becoming what intuition expects. Seen this way, the limits of intuition are no longer abstract. They are tangible. A solid object resting calmly in a room becomes a reminder that understanding deepens not by clinging to appearances, but by allowing evidence to reshape expectation. And once that reshaping begins, the strange quickly becomes coherent, even reassuring on its own quiet terms. Light feels straightforward. It illuminates spaces, reveals colors, and travels in ways that seem natural and uncomplicated. For a long time, it was described as a wave, spreading smoothly through space, much like ripples across water. This description worked beautifully, explaining how light bends, reflects, and creates interference patterns with elegant precision. By the late 19th century, the wave theory of light was considered one of physics' great achievements. And yet, even as this confidence grew, certain experimental observations began suggesting that something was missing from the picture. Waves, as they were understood, carried energy continuously. Brighten the light, and more energy arrives. Dim it, and less follows. Color or frequency should affect distribution, but not fundamentally change how energy is delivered. These expectations felt reasonable and were grounded in solid mathematical frameworks. But when light interacted with matter at very small scales, those expectations quietly failed. One of the clearest examples involved metal surfaces exposed to light. When certain metals were illuminated, electrons were ejected from their surfaces. This phenomenon, later called the photoelectric effect, had been observed before, but careful measurements revealed something deeply puzzling. The energy of ejected electrons did not depend on how bright the light was. Instead, it depended on color. Below a certain frequency, no electrons were released regardless of intensity. Increase brightness as much as desired and nothing happened, but raise the frequency beyond a specific threshold and electrons were ejected immediately, even when the light was faint. There was no gradual build-up, no delay. The effect appeared instantly. This behavior made no sense within a purely wave-based description. If energy arrived continuously, brighter light should eventually free electrons regardless of color. Experiments consistently showed otherwise. In 1905, Albert Einstein provided a crucial insight building directly on the idea of energy quantization. He proposed that light sometimes behaves as if it arrives in discrete packets, each carrying a specific amount of energy tied to its frequency. If a single packet carried enough energy, it could eject an electron. If it did not, no amount of additional light would help because energy was not pooled. It arrived one packet at a time, This was not a philosophical claim about the ultimate nature of light. It was a physical explanation for observed behavior. And it worked. The photoelectric effect followed naturally once light was treated as arriving in quantized units in this specific context. What made this proposal so unsettling was not that light behaved like a particle, but that it did so only in certain situations. In other experiments, light continued displaying unmistakable wave-like characteristics. Interference patterns appeared. Diffraction spread beams into predictable fringes. Reflection and refraction remained perfectly wave-like. There was no single description that fit all circumstances at once. This was not indecision on nature's part. It was consistency of a different kind. The behavior of light depended on how it was interacting with the world. When spreading freely or passing through apertures, wave descriptions captured its behavior precisely. When exchanging energy with matter at small scales, particle-like descriptions became necessary. The same entity obeyed different rules depending on the context of interaction. This is often described as wave-particle duality. Though the phrase can mislead, it suggests that light switches between identities as if choosing costumes. In reality, neither description is complete on its own. Waves and particles are human concepts, borrowed from familiar experience. Light does not commit exclusively to either. It simply behaves as experiments show it does, following rules that are consistent but not reducible to everyday categories. The photoelectric effect was not the only evidence pointing in this direction, but it was among the most decisive. It demonstrated that energy quantization applied directly to physical interactions between light and matter. Light could deliver energy only in discrete amounts, and matter responded accordingly. Einstein himself viewed this as a provisional step rather than a final picture. He recognized its necessity even while remaining uncertain about the broader implications that would follow. His contribution confirmed that quantization was not confined to abstract theoretical models. It was embedded in how light and matter actually interact. This shift carried a deeper message. Classical categories were beginning to fail. Waves and particles, long treated as distinct kinds of objects, were no longer sufficient as fundamental descriptions. They remained useful approximations but could not be applied universally without contradiction. The lesson here is subtle but important. Behavior is not an intrinsic label attached to an object. It emerges from interaction. Light does not carry a fixed identity, independent of circumstance. It reveals different aspects depending on what is being measured and how the measurement is arranged. There is quiet elegance in this idea. Nature is not inconsistent. Human language is. Trouble arises when descriptions developed for one domain are forced onto another where they no longer apply cleanly. When that happens, confusion follows. Not because reality is broken, but because expectations are misaligned. This understanding also builds naturally from energy quantization. If energy is exchanged in discrete amounts, then interactions must be described in ways that account for that discreteness. Waves alone cannot do this. Particles alone cannot capture interference. The deeper framework must accommodate both, without reducing either to metaphor. Gentle humor often helps soften this transition. Light, it seems, refuses to settle into a single role. It behaves impeccably, just not according to the categories preferred by intuition. Like a guest who follows every rule of the house while ignoring the seating chart, it remains polite but unpredictable. What matters is not how strange this feels, but how reliable it proves to be. Predictions based on this contextual behavior match experiments with extraordinary accuracy. Technologies that depend on light interacting with matter, from sensors to imaging systems, rely on these principles every day without incident. The rules may feel counterintuitive, but they are remarkably dependable. Scientific institutions around the world have tested these ideas under countless conditions. The results remain consistent. Light does not misbehave. It simply does not conform to classical categories. By accepting that behavior depends on interaction, a great deal of tension dissolves. The need to force light into a single identity fades. What remains is a clearer view of how nature operates at small scales, guided by quantization and shaped by context. This marks another step away from classical expectations. Matter is not solid in the way it appears. Energy does not flow continuously, and light, perhaps most strikingly, refuses to be only one thing. It follows rules that are precise, experimentally grounded, and quietly indifferent to how comfortable they feel. Smooth change feels natural. A fire dims gradually as fuel runs low. A light brightens slowly on a dimmer switch. Warmth seems to flow continuously, rather than arriving in discrete steps. This impression fits comfortably with everyday experience, where change appears infinitely divisible. For a long time, physics assumed the same. Energy, it was thought, could be added or removed in any amount, however small. Nature appeared to have no preference for tidy divisions. That assumption worked remarkably well across many situations. Classical physics described motion, heat, and electromagnetic radiation with impressive accuracy. Yet, as measurements grew more precise toward the end of the 19th century, cracks began appearing. Certain experiments refused to behave as expected. No matter how carefully calculations were adjusted, the smooth picture of energy began fraying at the edges. One of the most persistent problems involved something deceptively ordinary: glowing objects. Any warm material emits light. As temperature rises, the color and intensity of that glow change in predictable ways. This phenomenon, known as blackbody radiation, should have been straightforward to explain using classical theories. Classical theories predicted how much energy should be emitted at different wavelengths. Assuming energy flowed continuously, they were spectacularly wrong. According to classical predictions, a hot object should emit infinite energy at high frequencies, producing an ever-increasing amount of ultraviolet radiation. This outcome, later nicknamed the ultraviolet catastrophe, was not a minor discrepancy. It was complete failure. Real objects did not behave this way. Measurements showed that emitted energy rose to a peak and then declined smoothly without any runaway explosion. The problem was not experimental error. Laboratories across Europe reproduced the same curves repeatedly. The failure lay in underlying assumptions. Something about how energy was being treated did not match reality. In 1900, Max Planck approached the problem with considerable reluctance. He did not set out to revolutionize physics. His goal was to find a mathematical description that fit the data, nothing more. To do so, he introduced an idea he regarded as a temporary mathematical trick rather than a statement about nature. He proposed that energy could only be exchanged in discrete amounts proportional to the frequency of radiation. Instead of flowing smoothly, energy arrived in packets. At first, this felt absurd even to its author. There was no intuitive reason energy should behave this way. Nothing in everyday experience suggested it. Planck himself hoped the assumption could later be discarded, leaving the equations intact. But the equations worked precisely because of that assumption. Without it, they failed entirely. This marked the quiet birth of quantization. Energy, it seemed, was not infinitely divisible. It came in fixed units, now known as quanta. These units were not arbitrary. Their size was set by a constant of nature, a number so small that its effects only become noticeable at microscopic scales. At human scale, the steps are tiny enough to appear smooth, much like individual grains of sand blending into a continuous beach. The significance of this shift is difficult to overstate. Quantization was not an interpretation layered onto existing theory. It was a structural rule forced into place by experimental evidence. The universe itself appeared to insist on it. Once introduced, the idea began solving problems that had resisted explanation for years. Blackbody radiation curves matched observations perfectly. Heat capacity measurements at low temperatures began making sense. The strange behavior of light and matter at small scales started forming a coherent pattern. What is striking is how conservative this revolution was. Planck did not announce a new worldview. He followed the data where it led, even when it led somewhere uncomfortable. Quantization emerged not from imagination, but from necessity. It was a reluctant conclusion accepted because no alternative survived contact with experiment. This reluctance extended beyond Planck. Many physicists initially viewed quantization as a temporary patch, a clever fix awaiting deeper explanation. Yet as time passed, the pattern repeated. Whenever classical assumptions were applied to atomic-scale systems, predictions failed. Whenever energy was treated as coming in discrete amounts, predictions succeeded. Nature was consistent, even if the implications were unsettling. The idea of fixed energy exchanges deepened the departure from classical expectations already underway. Matter was no longer solid in the traditional sense. Now energy itself refused to behave as a smooth substance. Both insights pointed in the same direction. The familiar concepts that worked so well at large scales were becoming unreliable guides at small ones. There is subtle elegance in this. Quantization introduces order, not chaos. By limiting allowed energy values, it creates structure. Atomic stability depends on it. Without quantized energy levels, electrons would behave unpredictably. Atoms would collapse, and chemistry would dissolve into noise. The universe, as it turns out, relies on these tiny steps to remain coherent. Gentle humor can be found in how unintuitive this feels. A warm object does not emit heat in an endless drizzle, but in a disciplined sequence of microscopic drops. The steps are simply too small to notice without sensitive instruments. What seems continuous is often only continuous by approximation. Scientific institutions and laboratories worldwide have confirmed quantization through countless experiments. Spectroscopy reveals discrete lines where continuous bands were expected. Precision measurements of light and thermal behavior align perfectly with quantized models. Technology built upon these principles functions reliably every day, rarely drawing attention to the strange rules beneath its operation. Accepting quantization requires the same adjustment of intuition encountered before. Energy does not owe reality to familiarity. It follows its own rules, indifferent to whether they feel natural. Once this is accepted, confusion fades. What remains is quieter appreciation for how deeply structured the universe is, even where it appears smooth. Quantization stands as the first unmistakable signal that classical expectations have reached their limit. It is the point where continuity gives way to discreteness, not as a philosophical statement but as an experimentally enforced fact. From this foundation, the deeper architecture of quantum reality begins to take shape, one small step at a time, whether intuition approves or not. Certainty feels comforting. Release an object and it falls. Set something in motion and it follows a predictable path. For centuries, physics reflected this comfort. Given sufficient information about a system, the future could be calculated with precision. Positions determined velocities. Velocities determined trajectories. Trajectories determined outcomes. The universe appeared to unfold like machinery, each moment fully determined by the one preceding it. Quantum mechanics quietly breaks this expectation. At very small scales, even complete knowledge of a system does not allow prediction of a single definite outcome. Instead, it provides a range of possible results, each with a specific likelihood. Ask where a particle will be detected, and the answer is not a location, but a distribution. Ask when an atom will emit light, and the response is not a moment, but a probability. This is not a limitation of measurement. It is how the theory itself is structured. This shift can feel deeply unsettling initially. Probability is often associated with ignorance. A coin toss is uncertain because motion details are too complex to track. Weather forecasts rely on probability because atmospheric systems are chaotic. In these cases, probability stands in for missing information. If everything were known, certainty would return. Quantum mechanics does not work that way. Even in carefully controlled experiments repeated under identical conditions, outcomes vary. The same preparation leads to different results. Not because something was overlooked, but because variation is built into the fabric of the description. The theory does not say what will happen. It says what can happen and how likely each possibility is. This idea took time to settle into its modern form. Early formulations of quantum mechanics produced mathematical objects that behaved like waves, spreading through space and evolving smoothly over time. What those waves represented, however, was not immediately clear. They did not describe physical ripples like water waves. They were something else entirely. In the mid-1920s, Max Born offered a crucial interpretation. He proposed that these wave-like quantities did not represent matter itself, but probability. Specifically, they described the likelihood of finding a particle in a particular place if a measurement were made. The wave did not tell where the particle was. It told where the particle might be found. This was a profound conceptual step. It reframed the entire theory. The mathematics remained unchanged, but its meaning shifted. The smooth evolution of the wave described how probabilities evolved over time. When a measurement occurred, a single outcome appeared, selected from the range of possibilities according to those probabilities. Born's proposal was not philosophical decoration. It made direct contact with experiment. When physicists measured distributions of particles hitting screens, the results matched predicted probability patterns with remarkable accuracy. Individual events were unpredictable. Large numbers of events produced stable, repeatable distributions. This distinction matters. Quantum probability is not vague or approximate. It is precise. Experiments involving electrons, photons, and atoms confirm predicted probabilities again and again, often to extraordinary levels of precision. When millions of particles are measured, statistical patterns align perfectly with theoretical expectations. Uncertainty remains at the level of individual outcomes, not at the level of overall structure. This precision is one reason probability in quantum mechanics should not be confused with mere randomness. Randomness implies lack of pattern. Quantum systems display strong, reliable patterns, even while individual results remain unpredictable. The uncertainty lies not in the distribution, but in which member of that distribution will appear next. A helpful way to think about this is to reverse usual intuition. In classical physics, certainty comes first, and probability enters only when information is incomplete. In quantum physics, probability comes first, and certainty appears only when many events are considered together. The order is inverted. This inversion reframes earlier ideas about wave and particle behavior. When light produces an interference pattern, it does so statistically. Individual photons arrive as discrete events, each striking a single point. Over time, a pattern emerges. Not because each photon spreads out like a wave, but because the probabilities governing their arrival form a wave-like distribution. Seen this way, wave-particle duality becomes less puzzling. There is no need to imagine a single object switching identities. The wave describes probabilities. The particle describes outcomes. Both are essential, and neither alone tells the full story. This perspective also explains why quantum mechanics resists deterministic interpretation. The theory does not lack information about hidden variables waiting to be uncovered. Extensive experimental tests have shown that attempts to restore classical determinism fail. The probabilistic structure appears to be fundamental, not provisional. This was one of the most difficult aspects of quantum theory for many early physicists to accept. Albert Einstein famously objected to the idea that nature might be governed by chance, insisting that something deeper must be at work. Others shared his discomfort. Determinism had been a guiding principle for centuries, woven tightly into the identity of physics itself. Yet evidence continued pointing in the same direction. Experiments refined over decades supported Born's interpretation. Probability was not fading with improved measurement. It remained stubbornly central, no matter how carefully systems were prepared or how sensitive instruments became. There is quiet elegance to this outcome. Probability does not weaken the predictive power of quantum mechanics. It defines it. The theory tells exactly how often each outcome will occur, even if it cannot say which one will occur next. In many applications, this is more than sufficient. Lasers, semiconductors, and atomic clocks all rely on quantum probabilities behaving exactly as predicted. Scientific institutions and laboratories around the world test these predictions daily, often without drawing attention to deeper implications. Devices work because probabilities behave reliably. Engineers design systems confident that statistical outcomes will align with theory, and they do. Accepting probability as fundamental requires a gentle shift in expectation. The universe is not a machine that reveals its future, one inevitable step at a time. It is a system that offers possibilities constrained by precise rules and realized through interaction. Outcomes are not arbitrary. They are selected from a structured landscape of likelihood. There is even a certain kindness in this. Absolute determinism leaves no room for variation. Probability introduces flexibility without chaos. It allows systems to be stable on average while remaining open in detail. At small scales, this openness appears unavoidable. Gentle humor helps here as well. Nature, it seems, prefers to hedge its bets. It does not commit to a single outcome until asked. And even then, it follows a carefully weighted script rather than a rigid plan. The surprise is not that certainty disappears, but that so much order remains. By reframing wave-particle behavior in statistical terms, probability brings coherence, where confusion once lingered. Waves no longer need to be physical ripples. Particles no longer need predetermined paths. What exists between preparation and measurement is a set of possibilities evolving smoothly, waiting to be expressed. This marks a decisive shift away from classical determinism. The future is no longer a single line extending forward, but a branching field of potential outcomes shaped by precise mathematical rules. Understanding this does not diminish reality. It deepens it. Probability in quantum mechanics is not a statement about ignorance. It is a statement about how nature works. Once this is accepted, discomfort eases. What remains is a quieter, more flexible picture of the universe, one where certainty is not abandoned but redefined, emerging not from inevitability but from consistency across countless individual events. For much of scientific history, particles were imagined as basic units of reality. Small, solid points moving through empty space. Even as quantum mechanics complicated this picture, it remained tempting to imagine electrons, photons, and other particles as tiny objects with uncertain properties. The language of particles persisted because it felt familiar. It matched everyday experience scaled down. Modern physics quietly moves beyond that picture. At the deepest level currently understood, particles are not fundamental objects at all. They are disturbances, localized excitations of something more basic that fills all of space. That underlying structure is known as a field, and quantum field theory is the framework that brings this idea together. A field, in this context, is not a material substance. It is a continuous entity that exists everywhere, even in regions that appear completely empty. Temperature provides a familiar analogy at human scale. It exists throughout a room, varying smoothly from place to place. A magnetic field behaves similarly, stretching invisibly through space, influencing objects without occupying them physically. Quantum fields extend this idea to its most fundamental form. According to quantum field theory, every type of particle is associated with its own field. There is an electron field, a photon field, and fields for every other known particle. These fields are not optional additions. They are always present, even when no particles are detected. What is normally called a particle is simply a localized excitation in its corresponding field, much like a brief wave passing through an otherwise calm surface. This shift in perspective is profound. It replaces object-based thinking with process-based understanding. Instead of asking where a particle is, it becomes more accurate to ask how a field is behaving in a particular region. Instead of imagining objects moving through emptiness, reality becomes a tapestry of overlapping fields, continuously interacting and occasionally producing detectable excitations. This framework grew out of the need to combine quantum mechanics with special relativity. Early quantum theory worked well for isolated systems, but struggled to handle situations where particles could be created or destroyed, such as in high-energy collisions. Experiments showed that particles could appear and disappear, converting energy into matter and back again. A theory built around permanent objects could not accommodate this behavior cleanly. Quantum field theory solved this by treating creation and destruction as natural features. Fields can be excited or calm. Energy added to a field produces particles. Energy removed allows them to vanish. Nothing fundamental is lost or gained. The field remains. This view underlies the standard model of particle physics, the most successful description of fundamental interactions currently available. The standard model organizes known particles and forces into a coherent framework built entirely from interacting quantum fields. Electromagnetism, the weak nuclear interaction, and the strong nuclear interaction All arise from field interactions governed by precise rules. The predictive power of this model is extraordinary. Calculations based on quantum field theory match experimental results to astonishing accuracy. Certain quantities have been confirmed to more than 10 decimal places. This level of agreement is not accidental. It reflects a framework that captures something deeply real about how nature operates. Experimental confirmation of this picture comes from some of the most ambitious scientific efforts ever undertaken. Facilities such as large particle accelerators, operated by international collaborations, provide direct evidence for field-based behavior. At CERN, particles are accelerated to enormous energies and collided, briefly disturbing underlying fields enough to reveal new excitations. The results consistently support the field picture. New particles appear exactly where and when theory predicts. What is especially striking is that even empty space participates in this behavior. A region with no particles present is not inert. Fields are still there, fluctuating gently, constrained by quantum rules. These fluctuations can have measurable effects, confirming that fields are not abstract mathematical conveniences, but physically active components of reality. This understanding deepens earlier ideas about uncertainty and probability. If particles are excitations of fields, then uncertainty is no longer just about missing information. It reflects the fact that fields themselves have intrinsic variability. Probabilities describe how excitations emerge from continuous structures, not how objects hide their properties. It also reframes earlier confusion about wave and particle behavior. Waves are not optional descriptions layered onto particles. They are expressions of how fields evolve. The spread of a probability distribution reflects underlying field dynamics. When a particle is detected, it is not because a tiny object finally chose a location. It is because a field interaction produced a localized event. There is something quietly elegant about this. The universe is no longer a collection of things bouncing around in emptiness. It is a set of processes unfolding within ever-present structures. Fields interact, exchange energy, and produce the appearances labeled as particles. Objects become moments. Stability becomes pattern. Gentle humor fits here as well. The idea of particles turns out to be a useful illusion. Like waves on the ocean surface being mistaken for separate entities, the waves feel real, behave consistently, and can be measured precisely. Yet the deeper reality is the water itself. In quantum field theory, particles are the waves, fields are the ocean. This perspective also explains why the same particle can be created in different places under different conditions, yet always behaves identically. It is not because countless identical objects exist independently. It is because each excitation arises from the same underlying field, governed by the same rules everywhere. Scientific institutions across the world continue testing this framework, pushing it into new regimes of energy and precision. So far, it has held up remarkably well. Where it succeeds, it does so decisively. Where it encounters limits, it points clearly to questions that remain open. By replacing object-based thinking with field-based understanding, quantum field theory brings coherence to many strange features encountered earlier. Uncertainty, probability, and dual behavior all find a natural home within this deeper structure. The universe does not consist of tiny beads stitched together by force. It consists of fields continuously present, occasionally excited, and endlessly interacting. Once this shift is made, earlier discomfort begins to fade. The strange behavior of particles no longer feels like a series of exceptions. It becomes the expected behavior of a world built from fields rather than objects. And in that world, solidity, certainty, and individuality emerge not as fundamentals, but as patterns arising from a far richer and more subtle foundation. Separation feels fundamental. Two objects occupy different places. They move independently. What happens to one does not instantly affect the other. This assumption runs deep in everyday reasoning, reinforced by distance, time, and the apparent isolation of things in space. Even fields, continuous and overlapping as they are, still allow for local behavior where interactions diminish with distance. Quantum mechanics quietly unsettles this picture. There are situations where two particles cannot be described independently at all. Even when separated by vast distances, their properties become linked, not because of ongoing interaction, but because they share a single quantum description. This phenomenon is known as entanglement, and it represents one of the most striking departures from classical thinking. Entanglement does not mean particles communicate secretly or exchange signals faster than light. It means something subtler. The system must be treated as a whole. The state of one particle cannot be fully specified without reference to the other. What appears to be two objects behaving separately is, at a deeper level, one system expressing itself in two locations. This shared behavior arises naturally from the quantum framework already in place. When particles are created together or interact in specific ways, their properties become correlated. Measuring one reveals information about the other, not because information has traveled between them, but because the information was never separate to begin with. Consider a pair of particles produced in a single process. Their properties are linked by conservation laws. Before measurement, neither particle has a definite value for certain properties. Instead, the system as a whole has a well-defined structure. When one particle is measured, the system responds by producing a consistent outcome for the other, no matter how far apart they are. This is where intuition begins to struggle. Distance usually weakens influence. Here it does not. Correlations persist even when particles are separated by kilometers or more. Experiments have confirmed this repeatedly, using photons sent through optical fibers and free space, measured by detectors operating independently and far apart. The key word is correlation. Outcomes are linked in ways that cannot be explained by shared history alone. Classical explanations suggest particles might carry hidden instructions, predetermined responses merely revealed upon measurement. If that were the case, correlations would obey certain statistical limits. They do not. In the 1960s, physicist John Bell derived a set of inequalities that any theory based on local hidden variables must satisfy. These inequalities provided a clear experimental test. If measurements violated the inequalities, then no local explanation, based on preassigned properties, could account for the results. Experiments were carried out, again and again, with increasing sophistication and tighter controls. The inequalities were violated decisively. The results were unambiguous. Nature does not behave as if entangled particles carry independent instructions waiting to be uncovered. The correlations are stronger than any classical local theory allows. This does not mean information travels instantaneously. It means the underlying description is not built from independent parts. This is a crucial distinction. Entanglement does not allow faster than light communication. While measuring one particle affects the description of the system, it does not allow control over the outcome. Each individual result appears random. Only when results are compared later do the correlations become visible. No usable signal can be sent this way. This preserves consistency with relativity. Cause and effect remain bounded by the speed of light. What changes is not the flow of information, but the structure of description. The universe at small scales does not insist on separability as a fundamental principle. Seen through the lens of quantum fields, this becomes more intuitive. Fields extend throughout space. Excitations within them need not be independent if they arise from a shared process. Entanglement reflects the continuity of underlying fields rather than the independence of excitations. What appears as non-local behavior emerges naturally from a framework that was never fully local to begin with. This challenges the idea of objects as self-contained units. In the classical picture, objects possess properties internally, regardless of context. Quantum mechanics replaces this with a relational view. Properties are defined through interactions and shared states. Independence becomes an approximation, valid at large scales but incomplete at small ones. There is quiet elegance in this shift. It suggests that the universe is more interconnected than appearances suggest, without being chaotic or uncontrolled. Entanglement does not collapse space or erase distance. It reveals that some features of reality are distributed across systems rather than residing in isolated pieces. Gentle humor helps soften the surprise. Entangled particles behave less like distant strangers and more like dance partners who learn choreography together and continue in sync long after music has faded. No signals are exchanged. They simply remain coordinated because they were never separate in the first place. Experimental confirmation of entanglement has become routine in modern physics laboratories. Photons are entangled and sent in opposite directions. Measurements are made independently. Results align exactly with quantum predictions and consistently violate classical limits. These experiments are not rare demonstrations. They are standard tools used to test and refine understanding. The reliability of these results is what makes entanglement so important. It is not an exotic curiosity. It is a predictable feature of quantum systems. Technologies such as quantum cryptography rely directly on entanglement, using its correlations to detect interference and ensure security. The behavior is strange, but it is also dependable. This further reinforces the move away from object-based thinking. If particles were truly independent objects, entanglement would be impossible. The fact that it exists and exists reliably suggests that independence is not fundamental. It is emergent, arising when interactions fade and correlations become negligible. At human scales, this emergence is complete. Objects behave independently. Causes remain local. The classical world reasserts itself. At quantum scales, however, the seams remain visible. Systems retain memory of shared origins. Fields carry correlations across space without effort. Understanding entanglement requires patience, not reinterpretation of causality. Nothing travels faster than light. Nothing breaks the structure of space-time. What changes is the assumption that reality can always be divided cleanly into separate parts. This builds directly on earlier ideas about fields and probability. Probabilities apply not just to individual particles, but to entire systems. The wave description encompasses all entangled components at once. Measurement selects outcomes from the shared structure, producing results that appear local but reflect non-local organization. Once this is accepted, entanglement becomes less mysterious. It is no longer a paradox to be resolved, but a feature to be understood. The universe does not insist that everything be separable. It allows relationships to persist across distance, not through communication, but through shared description. In this way, entanglement quietly reshapes how reality is imagined. Objects are no longer the final units. Systems take precedence. Connections matter as much as components. And beneath the apparent independence of things lies deeper coherence, patiently expressed through correlations that refuse to fade, no matter how far apart their expressions may appear. Measurement sounds passive. Something is observed. A reading is taken. A value is recorded. In everyday life, measuring feels like a gentle act, a way of revealing what was already there. A thermometer does not change temperature. A scale does not alter weight. Observation appears separate from the thing being observed. Quantum mechanics quietly removes that separation. At small scales, measurement is not a neutral glance. It is a physical interaction. Energy is exchanged. Systems become linked. Outcomes are produced through contact, not revealed by inspection. Nothing mystical is required, and no special role is reserved for human awareness. What matters is not who looks, but what interacts. This distinction is essential because misunderstanding it has led to decades of unnecessary confusion. Popular accounts sometimes suggest that consciousness causes reality to crystallize, or that particles behave differently when watched. These ideas are compelling, but they are not supported by how quantum experiments actually work. Detectors do not need eyes. Screens do not need awareness. Atoms register outcomes just as effectively as people do. In quantum experiments, a measurement occurs when a system interacts with something large enough to leave a stable record. A photon strikes a detector. An electron triggers a signal. An atom emits light that is absorbed elsewhere. These interactions are physical processes governed by the same rules as everything else. No thought is required. The difficulty lies not in the act of measurement itself, but in how it fits into the broader description of quantum systems. Before measurement, systems are described by probabilities. After measurement, a specific outcome appears. The transition between these descriptions is what physicists call the measurement problem. It is important to note what this problem is not. It is not a question about human perception. It is not about when someone becomes aware of a result. It is about how a probabilistic description gives rise to a single event. Early architects of quantum theory were acutely aware of this tension. Niels Bohr, one of the central figures in its development, emphasized that quantum systems cannot be separated from the conditions under which they are measured. According to what became known as the Copenhagen interpretation, physical properties are not attributes carried independently by particles. They are defined through interaction. This does not mean that reality depends on observers. It means that descriptions depend on context. The arrangement of an experiment determines what can meaningfully be said about a system. Change the interaction, and different properties become relevant. Bohr argued that it is a mistake to imagine quantum objects possessing a complete set of definite properties at all times. Some properties only become well-defined when measured. Others remain undefined, not because they are hidden, but because the situation does not allow them to exist simultaneously. This view aligns naturally with everything encountered so far. Probability replaces certainty. Uncertainty limits simultaneous definition. Fields underlie particles. Entanglement links systems across distance. Measurement fits into this picture, not as an intrusion, but as participation. When a quantum system is measured, it becomes entangled with the measuring device. The system and apparatus form a combined whole. From the perspective of the apparatus, a definite outcome appears. From the perspective of the larger quantum description, the interaction has produced a stable correlation. This is why disturbance is not the right word. Measurement does not simply knock a system out of its natural state. It creates a new state that includes both system and measuring device. The outcome is not uncovered. It is produced through interaction. A helpful everyday analogy is dialogue. Words do not exist as fixed objects waiting to be discovered. They arise through interaction between speakers. Once spoken, they become part of the shared environment. Measurement is similar. It is an event that brings something into being within a particular context. This perspective also dissolves much of the confusion surrounding collapse. The idea that a wave function suddenly collapses can sound dramatic, even violent. In practice, it describes the transition from a probabilistic description to a definite record. Once an outcome is registered in a stable way, probabilities are no longer needed to describe that particular event. Nothing special happens at the moment of human awareness. The outcome exists as soon as it is registered physically. Consciousness enters later, reading a result that has already taken place. This understanding is supported by countless experiments. Automated detectors register quantum events without supervision. Data is stored, analyzed later, and compared across laboratories. The results do not wait for observation. They are produced by interaction and preserved by physical systems. The measurement problem remains an active area of research, not because measurement is mysterious, but because the boundary between quantum and classical descriptions is subtle. Large systems behave classically, not because quantum rules stop applying, but because interactions spread information so widely that probabilistic descriptions become effectively irreversible. Once information about an outcome is dispersed into many degrees of freedom, the system behaves as if a single result has been selected permanently. This is why measuring devices appear classical. They are designed to amplify tiny events into robust records. Understanding measurement in this way also clarifies its relationship to entanglement. Measurement is a special case of entanglement, where one part of the system is large, stable, and capable of recording outcomes. The correlations produced become one-sided, favoring definite records over reversible evolution. Gentle humor fits here too. The universe does not wait to be noticed. It does not pause politely until someone looks. Measurements happen because things bump into other things, exchange energy, and leave traces behind. Awareness arrives afterward, like reading yesterday's news. Stabilizing the concept of measurement removes a great deal of unnecessary tension from quantum mechanics. There is no need to invoke consciousness as a causal agent. There is no need to imagine reality flickering in and out of existence. There is only interaction governed by precise rules, producing outcomes that become part of the physical world. This view also restores continuity with the rest of physics. Measurement is not a special category reserved for quantum systems. All measurement at every scale involves interaction. The difference is that at small scales, interaction cannot be ignored or treated as negligible. Seen this way, measurement is not an obstacle to understanding quantum reality. It is one of its most revealing features. It shows how possibilities become events, how probabilities give way to records, and how the abstract structure of the theory connects to the concrete world. By emphasizing participation rather than disturbance, measurement becomes less threatening and more coherent. It is not an act of interference that breaks a delicate system. It is the natural way systems relate to one another. Once this is appreciated, lingering mystery softens. Measurement is no longer the point where physics gives up. It is the point where interaction becomes visible. And in that visibility, the quiet logic of quantum mechanics continues to hold. Consistent, testable, and firmly grounded in the physical world, quantum mechanics has an unusual reputation. It is one of the most successful theories ever developed, yet it is also one of the most debated, not because its predictions fail, but because its meaning remains open to interpretation. This combination can feel unsettling. In most areas of science, disagreement signals uncertainty or incomplete understanding. Here, disagreement persists, even while the mathematics works flawlessly. The reason is subtle. Quantum mechanics is extraordinarily clear about what will be observed. It is far less explicit about what is happening in between. The equations describe how probabilities evolve over time. They specify how systems behave when they interact, and what outcomes will be produced. These rules have been tested for over a century and confirmed with remarkable precision. Wherever experiments have been performed carefully, results align with the same mathematical framework, and yet that framework allows more than one way of telling the story. This is why multiple interpretations exist. The mathematics does not dictate a single narrative about what reality is doing when it is not being measured. It tells how to calculate results, not how to imagine the underlying process. Different interpretations step into that gap, offering distinct ways of thinking about the same formal structure. One of the earliest and most influential approaches is commonly known as the Copenhagen interpretation, associated with figures such as Niels Bohr. It emphasizes the role of measurement and context. In this view, quantum systems do not possess definite properties independent of interaction. Physical quantities become meaningful only when measured, and the theory concerns what can be said about outcomes, not what exists unobserved. Copenhagen thinking is often pragmatic. It does not attempt to describe an underlying mechanism behind the equations. Instead, it treats the mathematical framework as complete in itself. Questions about what happens between measurements are considered either undefined or unnecessary. This approach has the advantage of restraint. It avoids adding assumptions beyond what experiments require. For some, however, this restraint feels unsatisfying. The desire to describe an objective reality unfolding continuously has a long history in physics. This motivation gave rise to alternative interpretations that retain the same mathematics while telling a different story. One such approach is the many worlds interpretation, proposed by Hugh Everett in the 1950s. Instead of treating measurement as a special event where probabilities collapse into a single outcome, this view suggests that all possible outcomes occur. Each outcome corresponds to a different branch of the universe, all evolving according to the same underlying equations. In this picture, probability reflects the relative weight of these branches rather than the chance of a single outcome. There is no collapse. The wave description continues smoothly and universally. Measurement becomes a process of branching rather than selection. This idea can sound extravagant, even overwhelming, yet it does not introduce new mathematics. It takes the existing equations at face value and applies them universally, including to measuring devices and observers. Its boldness lies in interpretation, not prediction. At the other end of the conceptual spectrum lies pilot wave theory, associated with David Bohm. This approach reintroduces determinism by proposing that particles have definite positions at all times, guided by an underlying wave. The wave evolves according to standard quantum equations, while particles follow precise trajectories influenced by it. In this view, probability arises from ignorance about initial conditions rather than fundamental indeterminacy. The wave provides the structure. The particle provides the outcome. Both coexist, linked by clear rules. Pilot wave theory restores a sense of continuous motion and objective reality. However, it does so at a cost. It requires non-local influences, where changes in one part of the system can affect distant parts instantaneously. While this does not allow faster-than-light communication, it challenges intuitive notions of locality. What is remarkable is that all of these interpretations agree on what experiments will show. Whether one prefers Copenhagen restraint, Everett branching, or Bohmian guidance, the calculated probabilities are identical. No experiment currently distinguishes between them. This is not a weakness of quantum mechanics. It is a reflection of its completeness. The theory provides all the information needed to predict outcomes. The interpretations differ only in how that information is framed conceptually. This distinction between physics and philosophy is essential. Physics concerns testable predictions. Philosophy concerns meaning, explanation, and intuition. Interpretations belong primarily to the second category. They influence how the theory is understood, taught, and imagined, but they do not alter its empirical success. This is why debates about interpretation can persist indefinitely without being resolved by experiment. They are not disagreements about facts. They are disagreements about how to narrate those facts. There is a temptation to treat one interpretation as more correct than others. Often this preference reflects personal taste. Some find comfort in minimalism, others prefer realism. Some are drawn to determinism. Others accept indeterminacy as fundamental. The mathematics remains indifferent to these preferences. Gentle humor helps here. Quantum mechanics is like a perfectly accurate recipe that refuses to explain why the dish tastes the way it does. Different cooks invent different stories about the flavor, but the meal comes out the same every time. Understanding this can be liberating. It removes the pressure to choose the right interpretation. One can work effectively with the theory without committing to a particular metaphysical stance. Many practicing physicists do exactly that, using the mathematics daily while remaining agnostic about its deeper meaning. This also reframes earlier debates about measurement. Whether one views measurement as collapse, branching, or guidance, the observable results are the same. The differences lie in how one imagines the unseen processes connecting preparation to outcome. By separating physics from philosophical framing, much of the tension surrounding quantum mechanics dissolves. The theory does not demand belief in any particular story. It demands only that its rules be followed when making predictions. This separation also reflects scientific humility. Quantum mechanics tells what can be known and calculated with extraordinary precision. It remains silent on certain questions, not because it is incomplete, but because those questions may not have operational meaning within the theory. Seen this way, multiple interpretations are not a sign of confusion. They are a sign of flexibility. The same mathematical structure supports different ways of thinking, each consistent with observation. The universe, it seems, is content to be calculated correctly without insisting on a single explanation. The equations do their work quietly and reliably. The stories built around them remain optional. And in that quiet separation between calculation and interpretation, quantum mechanics reveals something subtle. Understanding does not always require agreement on meaning. Sometimes it requires only that predictions be precise, experiments be honest, and expectations remain open to more than one way of seeing the same underlying structure. Quantum mechanics is often discussed as if it lives at the edges of reality, tucked away in laboratories and abstract equations, far removed from ordinary life. It can feel like a theory reserved for extremes, for particles moving at enormous speeds or systems chilled close to absolute stillness. And yet quantum rules are woven quietly into the fabric of everyday technology, operating reliably and unnoticed, often billions of times per second. The most striking thing about these technologies is not how strange they are, but how dependable they have become. Consider the transistor. It is difficult to imagine modern life without it. Every smartphone, computer, router, and digital device depends on vast numbers of transistors working together in precise coordination. They switch currents on and off, amplify signals, and perform logical operations with extraordinary consistency. A single modern processor may contain billions of them, each one smaller than a microscopic speck. None of this would be possible without quantum mechanics. Transistors rely on the behavior of electrons in solids, particularly how they move through materials known as semiconductors. Classical physics cannot explain why some materials conduct electricity while others do not, or why adding small amounts of impurities dramatically changes electrical behavior. Quantum mechanics provides the answer by describing how electrons occupy allowed energy bands within a material. In a semiconductor, electrons can exist only at specific energy levels. By carefully controlling these levels through material design, engineers create regions where electrons can flow freely and regions where they are blocked. The transistor works by nudging electrons between these allowed states, using small electrical signals to control much larger currents. This process depends entirely on quantized energy levels and probability-based electron behavior. What matters here is not novelty, but reliability. Transistors do not work most of the time. They work, essentially, all the time. Their behavior is so predictable that engineers design systems assuming failure rates so low they are practically negligible. This confidence comes from quantum theory doing exactly what it says it will do. Lasers offer another clear example. Laser light is not just bright, it is coherent, meaning the light waves are aligned in an exceptionally orderly way. This property allows lasers to cut metal, transmit information through optical fibers, scan barcodes, and perform delicate surgery. The operation of a laser depends on stimulated emission, a process predicted by quantum mechanics. Atoms or molecules are placed into excited energy states. When a photon of the right energy passes by, it triggers the release of another photon with identical properties. Direction, frequency, and phase all match. The result is a cascade of perfectly coordinated light. This behavior cannot be explained without discrete energy levels. Atoms must have well-defined transitions. Photons must carry specific amounts of energy. Probability governs when emission occurs, but the structure of the process ensures that the outcome is highly ordered. Once again, the remarkable feature is not that this works at all, but that it works every time. Lasers operate continuously in factories, hospitals, and communication networks with extraordinary stability. The underlying quantum processes are not delicate curiosities. They are robust enough to be engineered, scaled, and trusted. Medical imaging provides a more subtle illustration. Magnetic resonance imaging, often shortened to MRI, allows detailed images of the interior of the body without surgery. It relies on the quantum properties of atomic nuclei, particularly how they respond to magnetic fields and radio frequency pulses. Nuclei possess intrinsic magnetic behavior that arises from quantum properties. When placed in a strong magnetic field, they align in specific ways. Applying carefully tuned pulses causes them to shift between allowed states. As they return to equilibrium, they emit signals that can be detected and translated into detailed images. This process depends on quantization, probability, and interaction. The signals are weak, the calculations are complex, yet the results are precise enough to distinguish soft tissue from bone, healthy cells from diseased ones. Hospitals rely on these machines daily, confident that the physics beneath them will behave exactly as expected. Behind all of this lies an enormous body of applied research. Universities, engineering institutions, and industrial laboratories have spent decades refining quantum principles into practical tools. This work is rarely dramatic. It involves careful calibration, incremental improvement, and relentless testing. The goal is not to explore philosophical implications, but to make devices that function reliably in real environments. What is striking is how little attention the quantum strangeness itself receives once a technology is mature. Engineers do not worry about wave-particle duality when designing circuits. Doctors do not contemplate probability distributions while reading MRI scans. The quantum rules have been absorbed into the background, trusted implicitly. This trust is earned. Quantum mechanics has been subjected to more experimental verification than almost any other theory in science. Its predictions have been tested across countless systems and conditions. Where it applies, it applies with extraordinary accuracy. There is gentle humor in how this contrasts with its reputation. A theory often described as confusing and mysterious underpins some of the most reliable machines ever built. The universe may behave strangely at small scales, but it does so with remarkable consistency. This consistency reinforces an important point. Quantum mechanics is not fragile. It does not fall apart when applied. It does not require constant reinterpretation to function. Once the rules are understood, they can be used confidently. The purpose of grounding abstraction in daily life is not to diminish the wonder of quantum theory, but to place it in context. The same principles that challenge intuition also make modern technology possible. The same uncertainty that unsettles philosophy stabilizes atoms, enables chemistry, and supports complex engineering. Reliability emerges not despite quantum behavior, but because of it. Probability distributions behave predictably in large numbers. Energy levels remain fixed. Interactions follow strict constraints. Engineers build systems that exploit these features rather than fighting them. Scientific bodies and engineering organizations around the world continue to expand this toolkit. Research into quantum materials, precision measurement, and controlled quantum systems pushes technology forward steadily. Much of this progress happens quietly, without fanfare, as ideas move from theory to application to infrastructure. This quiet integration is perhaps quantum mechanics' greatest success. It has moved from a theory that challenged intuition to one that supports daily life without demanding attention. Its strangeness fades into reliability. Its abstraction becomes routine. Seen this way, the journey from atomic uncertainty to everyday technology feels less surprising. Once it is accepted that quantum rules govern matter at its most basic level, it becomes natural that those rules shape everything built from that matter. Computers compute because electrons behave as quantum mechanics predicts. Lasers shine because atoms release energy in quantized steps. Medical images form because nuclei respond to magnetic fields in precise probabilistic ways. None of this is accidental. It is the direct consequence of a theory that describes reality accurately, even when that description feels unfamiliar. By reinforcing theory through application, quantum mechanics reveals its true character. It is not an exotic add-on to physics. It is the foundation upon which much of modern technology rests. And perhaps the most reassuring lesson of all is this: a universe governed by probability, uncertainty, and fields is not unreliable. It is dependable in ways that classical intuition never anticipated. The same rules that blur trajectories and soften certainty also power devices that rarely fail. Quantum mechanics does not merely explain the world, it runs it, quietly and consistently, every day. Quantum mechanics has earned its reputation for reliability. Its predictions have been tested across an enormous range of experiments, from atomic spectra to semiconductor behavior, from lasers to medical imaging. Where it applies with extraordinary precision. It is tempting, after such success, to imagine it as complete. And yet even the most powerful theories have edges, places where the assumptions that make the theory work begin to strain. Quantum mechanics does not explain everything. It was never meant to. Its limits are not failures so much as boundaries. Recognizing those boundaries is not a weakness of science, it is one of its strengths. One of the clearest limits appears when gravity enters the picture. Quantum mechanics describes matter and energy at very small scales. General relativity describes gravity, space-time, and the large-scale structure of the universe. Each theory works beautifully in its own domain. Quantum mechanics excels at the microscopic. Relativity excels at the cosmic. Trouble arises when situations demand both at once. Consider environments where enormous mass is packed into extremely small regions, the centers of black holes, the earliest moments of the universe. In these settings, gravity is intense, and quantum effects cannot be ignored. Space and time themselves become dynamic, while quantum uncertainty remains unavoidable. Neither theory on its own can fully describe such conditions. Quantum mechanics assumes a fixed background of space and time. Relativity treats space-time as something that bends, stretches, and responds to energy. Trying to apply quantum rules to a geometry that is itself fluctuating leads to mathematical inconsistencies. The equations resist combination. Predictions lose clarity. This mismatch is often referred to as the problem of quantum gravity. It is important to be clear about what this does and does not mean. Quantum mechanics does not suddenly stop working in everyday situations. Atoms remain stable. Technologies remain reliable. Even strong gravitational fields encountered in most astrophysical settings can be handled using approximations that work extremely well. The breakdown appears only in extreme regimes, far beyond direct experimental reach. At the center of a black hole, densities become so high that classical spacetime description breaks down. In the earliest fraction of a second after the universe began, energy densities were so extreme that quantum fluctuations of spacetime itself may have dominated behavior. In these regimes, existing theories provide hints, but not complete answers. Physicists have known about this gap for decades. It is not a surprise. It is a signpost. Many approaches have been developed to address it. Some attempt to quantize gravity directly, treating spacetime itself as subject to quantum rules. Others suggest that gravity may emerge from deeper structures, not yet fully understood. Each approach tackles the same problem from a different angle, searching for a framework that remains consistent where current theories overlap. Large research collaborations across the world are involved in this effort. International teams bring together expertise in particle physics, cosmology, mathematics, and computation. Observatories study black holes and gravitational waves. Particle accelerators probe high-energy interactions. Precision experiments test the limits of existing theories with increasing sensitivity. Despite this effort, no final theory has yet emerged. This is not a failure. It reflects the difficulty of the task. Nature does not reveal its deepest structure easily, especially when the relevant scales are far removed from everyday experience. The history of physics suggests that such transitions take time. Classical mechanics was not replaced overnight. Quantum theory itself emerged gradually, shaped by decades of experiment and debate. There is also quiet humility built into this moment. Quantum mechanics has not been overthrown. It remains accurate where it applies. Relativity has not been discarded. It continues to describe gravity with stunning success. The challenge lies not in fixing broken theories, but in understanding how two successful descriptions fit together. This perspective matters because it prevents misunderstanding. Limits do not imply error. They imply scope. A map of a city is not wrong because it does not show the entire planet. It is accurate within its intended range. Quantum mechanics is a map of the microscopic world. It becomes less informative when asked to describe the geometry of space-time itself. That does not diminish its value. It clarifies its role. Gentle humor can help here. Even the most impressive tools have instruction manuals. Quantum mechanics, for all its power, comes with a quiet note in the margins that reads, "Results may vary near singularities." Acknowledging boundaries honestly also stabilizes interpretation debates. Some disagreements about meaning arise from pushing the theory beyond where it was designed to operate. When questions wander into regimes where quantum mechanics and gravity collide, ambiguity is inevitable. The mathematics itself signals that something new is required. This realization prepares the ground for reflection rather than frustration. Science progresses not by pretending answers exist where they do not, but by recognizing the shape of the unknown. Boundaries guide inquiry. They tell researchers where to look next. It is also worth noting that these limits are extraordinarily remote from daily life. The absence of a complete theory of quantum gravity does not affect chemistry, biology, or technology. The stability of matter remains intact. The predictions of quantum mechanics remain reliable across an enormous range of conditions. The gap appears only when asking questions at the absolute extremes of scale and energy. Questions about the origin of the universe. Questions about the interior of black holes. Questions about whether space and time themselves have quantum structure. These are not practical problems, they are foundational ones. There is something quietly reassuring in this. The universe is not failing to make sense. It is simply more layered than current theories can fully capture. Each layer reveals new structure while preserving the reliability of the layers above it. This layered view fits naturally with everything encountered so far. Intuition fails at small scales, yet understanding deepens. Uncertainty limits precision, yet stability emerges. Space and time become subtle, yet experience remains coherent. Boundaries appear not as dead ends, but as invitations. Scientific institutions continue to approach these questions with care. The language used is cautious. Claims are restrained. Progress is measured not in dramatic announcements, but in improved consistency, refined mathematics, and clearer connections between ideas. This restraint is intentional. History has shown that rushing conclusions in foundational physics rarely ends well. The universe rewards patience. By acknowledging where quantum theory stops working, the narrative shifts gently from explanation to reflection. It becomes possible to appreciate how much has been understood without demanding immediate closure. The unknown is framed not as a gap to be filled hastily, but as a horizon to be approached thoughtfully. This honesty also reinforces trust. A theory that openly acknowledges its limits is more reliable than one that claims completeness prematurely. Quantum mechanics has earned confidence precisely because it makes clear statements about where it applies and remains silent where it does not. As the exploration draws closer to its end, this perspective becomes increasingly important. Understanding does not require final answers to every question. It requires clarity about what is known, what is unknown, and why the distinction matters. Quantum mechanics stops working not because it fails, but because reality continues beyond its current reach. That continuation is not a threat to coherence. It is a reminder that science is an ongoing process, one that advances by respecting both its achievements and its boundaries. In recognizing where theory ends, a quieter insight emerges. Knowledge is not diminished by acknowledging limits. It is strengthened, and within those limits, quantum mechanics remains one of the most reliable guides ever developed, even as it points calmly toward questions still waiting for their turn to be answered. Ignorance usually carries negative weight. To admit not knowing can feel like weakness, hesitation, or failure. In everyday settings, uncertainty is something to be resolved quickly, smoothed over, or hidden behind confidence. Science, however, treats ignorance very differently. It treats it as a signal, a marker, often as an invitation. Some of the most important advances in physics began not with answers, but with discomfort. Observations that did not fit expectations, measurements that refused to align with trusted models, results that felt wrong, not because the data were flawed, but because the ideas used to interpret them were no longer sufficient. This pattern appears again and again. At the end of the 19th century, physics was widely regarded as nearly complete. The laws of motion were known. Electromagnetism had been unified. Many believed that only small refinements remained, and yet experimental puzzles were quietly accumulating. Heat radiation behaved oddly. Atomic spectra showed unexplained lines. Light produced effects no one could account for. These were not dramatic mysteries. They were technical irritations, minor inconsistencies that refused to disappear. Rather than ignoring them, physicists leaned into the confusion. They treated the mismatch between theory and experiment not as an embarrassment, but as a clue. That willingness to sit with uncertainty allowed something new to emerge. Quantum mechanics did not arise because everything made sense. It arose because something clearly did not. The same is true throughout the history of science. Classical mechanics worked brilliantly until it didn't. Newton's laws described motion with extraordinary accuracy, yet subtle discrepancies accumulated in planetary orbits. Those discrepancies did not invalidate the theory. They revealed its limits. From that revelation came a deeper understanding of gravity. Ignorance in this sense is not a void. It is structured. It has shape. It points toward where existing ideas are stretched too thin. What distinguishes science from guesswork is how this ignorance is handled. It is not filled with speculation for its own sake. It is not ignored in the hope that it will go away. It is documented, tested, and revisited. Questions are sharpened rather than blurred. Assumptions are examined rather than defended. This requires humility. Humility in science does not mean doubting everything or refusing to commit to conclusions. It means recognizing that even the best theories are provisional. They are maps, not territory. They describe reality within a certain range, and outside that range, their guidance fades. Quantum mechanics exemplifies this attitude. It makes extraordinarily precise predictions where it applies. At the same time, it openly acknowledges where it cannot yet speak. It does not pretend to explain the origin of space-time or the deepest structure of gravity. It leaves those questions open, not as failures, but as boundaries. This openness is not passive. It drives research. Entire fields of physics exist because someone was willing to say, "This does not quite work." Particle accelerators were built to explore gaps in understanding. Space telescopes were launched to probe anomalies in cosmic behavior. Precision experiments were designed to test assumptions thought to be settled. Each of these efforts began with uncertainty. There is a temptation to think of scientific progress as a steady march toward complete knowledge. In practice, it looks more like a series of adjustments. Periods of clarity are followed by moments of confusion. Each time confusion appears, it marks the edge of a framework that has done its job. Seen this way, not knowing is not an obstacle to progress, it is its engine. Gentle humor helps here. If science only advanced when everyone felt confident, it would have stopped centuries ago. Progress depends on a certain tolerance for being wrong, or at least incomplete. The universe rarely rewards certainty with new insight. It responds better to careful doubt. This perspective also stabilizes the emotional experience of open questions. It is easy to feel unsettled by the idea that fundamental aspects of reality remain unexplained. What is time really? Why does gravity resist quantization? What lies beyond current theories? These questions can feel like loose ends. Science treats them differently. Open questions are not loose ends. They are guideposts. They help prioritize effort. They shape experiments. They encourage collaboration across disciplines. They prevent stagnation by reminding researchers that understanding is always in progress. Importantly, this does not mean that everything is uncertain. Much is known with extraordinary confidence: the stability of atoms, the behavior of electrons in materials, the rules governing chemical reactions. These foundations are not shaken by unanswered questions at deeper levels. Ignorance coexists with knowledge. The two are not opposites. They define one another. This coexistence is one of science's quiet strengths. It allows confidence without arrogance, precision without finality. Theories are trusted where they work and questioned where they do not. Historically, the moments when science advanced most dramatically were often those when ignorance was faced directly rather than avoided, when unexpected results were published rather than dismissed, when confusion was treated as meaningful rather than inconvenient. This attitude is not limited to physics. It appears throughout scientific practice. In medicine, unexplained symptoms drive discovery. In biology, anomalies lead to new understanding of life's complexity. In climate science, uncertainties guide the development of better models. In every case, ignorance functions as a tool. It narrows attention. It sharpens questions. It motivates careful measurement. Without it, science would become a catalogue of accepted facts, disconnected from discovery. There is also a deeper philosophical comfort in this approach. It acknowledges that the universe does not owe complete transparency. Understanding unfolds gradually, shaped by what can be measured and tested at a given time. Expecting total clarity is not a scientific requirement. It is a human preference. Quantum mechanics has repeatedly taught this lesson. Each time intuition failed, deeper structure emerged. Each time certainty dissolved, stability was found at a new level. Uncertainty did not signal collapse. It signaled transition. By reframing ignorance as progress rather than deficiency, the narrative changes. Open questions no longer feel like gaps in reality. They feel like the next steps in a process that has always moved forward by questioning itself. This reframing also invites patience. Some problems take decades, others may take centuries. Some may require entirely new ways of thinking. Science is comfortable with that timescale. It is not in a hurry. The purpose here is not to romanticize confusion, but to normalize it. Confusion is not the enemy of understanding. It is often its starting point. As the exploration draws nearer to its conclusion, this perspective becomes especially valuable. The absence of final answers does not diminish what has been learned. It contextualizes it. It reminds that knowledge grows by expanding into the unknown, not by pretending the unknown is smaller than it is. Ignorance handled carefully becomes one of the most powerful tools science possesses. It keeps inquiry honest, it keeps curiosity alive, and it ensures that progress remains possible even when certainty feels out of reach. In that sense, not knowing is not a flaw in the scientific story. It is one of its defining features. At the smallest scales ever explored, matter no longer behaves in ways everyday intuition would suggest. Properties appear only through interaction. Patterns emerge that follow clear rules, yet resist simple cause and effect. What seems stable from a distance becomes fluid up close, guided less by certainty than by disciplined tendency. Throughout this journey, quantum mechanics has revealed itself not as a theory of chaos, but as a theory of structure. Structure that is subtle, constrained, and extraordinarily reliable, even when it feels strange. Again and again, the same pattern has appeared. Intuition fails. Deeper order emerges. What seemed impossible becomes consistent. Measurement remains dependable. Predictions align with experiment. Technologies function without hesitation. Whatever reality may be doing beneath the surface, it does so with remarkable discipline. This reliability is easy to overlook amid discussions of interpretation and mystery. It is tempting to focus on what is unresolved, on questions that remain open, or descriptions that feel incomplete. Yet every experiment ever performed within the domain of quantum mechanics has returned results that fit the same underlying framework. The theory does not wobble when interpretations diverge. It does not depend on agreement about meaning to function correctly. Standing at the edge of quantum understanding does not feel like standing before a void. It feels more like pausing at a shoreline where familiar ground gives way to deeper water, and where the surface remains calm even as unseen structures extend below. After following quantum ideas through uncertainty, probability, fields, entanglement, and limits, what remains most striking is not how unstable reality becomes, but how reliably it holds together. There is quiet reassurance in this. The universe does not change its rules depending on whether they feel comfortable. It behaves consistently, patiently, and without regard for expectation. When intuition falters, it is not a sign that reality is broken. It is a reminder that understanding must be extended, not assumed. Quantum mechanics at its boundary leaves understanding open in a way that is calm rather than troubling. It invites patience. It allows questions to remain active without becoming urgent. It suggests that knowledge can be strong without being total, and that coherence does not require closure. The laws of physics do not flicker at the edge of understanding. They continue smoothly, governing interactions, structures, and change with quiet consistency. What shifts is perspective. What changes is the way meaning is drawn from behavior. There is subtle comfort in accepting this. A universe that admits mystery without surrendering reliability is not fragile. It is resilient. It allows understanding to grow without demanding finality. It supports precise knowledge where precision is possible. And it leaves space where new ideas may one day take shape. Mystery in this context does not erode reality. It deepens it. Knowing that the vacuum is active does not make space feel emptier. It makes it richer. Knowing that uncertainty underpins stability does not make matter feel less real. It makes its persistence more remarkable. Knowing that interpretations differ does not weaken physical law. It highlights how strongly that law holds beneath varied descriptions. Quantum theory teaches that meaning is not always found in definitive pictures. Sometimes it emerges from limits, from knowing what cannot be asked cleanly, from recognizing where language reaches its edge. These limits do not block understanding. They shape it. This shaping is gentle rather than dramatic. There is no sudden loss of coherence at the quantum scale. There is no collapse of order. What appears instead is a steady transition from familiar intuition to careful structure. reality continues to behave consistently even as explanation becomes more abstract. Ending without resolution does not mean ending without reassurance. The absence of final answers does not imply instability or incompleteness in the world itself. It reflects the nature of inquiry, not the fragility of existence. The universe does not wait for explanation to function. It functions first. An explanation follows where it can. Quantum mechanics at its boundary reveals not a theory pulling the ground away beneath reality, but one showing how firm that ground is, even when its deepest layers remain unseen. It shows that mystery is not a crack in the foundation, but part of its design. And so the journey does not end with an answer. It settles instead into a view, one where reality is stable, law is continuous, and understanding is allowed to remain unfinished. One where the unknown is not a threat but a horizon, and at that horizon there is no urgency, only space to pause, to reflect, and to recognize that the universe, even at its most elusive, remains quietly, patiently, reliably itself. Good night, better sleep, a lighter day.